Hi everyone, welcome back to chemistry. In this video, I just wanted to film a quick video looking over some review questions for your exam tomorrow. So last class we did some review questions from chapter 8 and 9, and this time I want to talk about chapters 9 and 10. So this first question is regarding chapter 9 material, and it says, arrange the following group of atoms in order of increasing first ionization energy, or IE1. So first ionization energy, let's remind ourselves first of what that measures. So this is a measure, or a measure of the amount of energy required to remove an electron. So really what we're looking for, if we're looking to place these in order of increasing ionization energy, we want to figure out which atoms are likely to want to give up an electron, and which are likely to try to hang on to their electron, or which are going to be resistant to that. So we kind of learned a trend that might help us out since we don't have any data to look at for these atoms. And let me remind myself, so we've got silicon, chlorine, and sodium. So let me just highlight those. We've got silicon, chlorine, and sodium. So it looks like, we do know a trend going from the left to the right. We know that our ionization energy, increases going from the left to the right. And we said that there's kind of like a couple ways that you could think about it. But one of the things is, or one of the ways that we could kind of reason this out or explain this trend is we've got increasing nuclear charge as we go from the left to the right. So remember that the effective nuclear charge for these different elements depends on how many protons that they have in their nucleus, right? So sodium has 11, silicon has 14, and chlorine has 17. So you could calculate the effective nuclear charge, but you actually don't really need to in this case, because it follows the trend really nicely. But if you wanted to, you could, and it would kind of reinforce this trend here. But the idea is that if, for instance, chlorine has more protons in its nucleus, but its shielding electrons are about the same, or its shielding is about the same, then those core electrons are going to be held much closer to the nucleus than something like sodium. So that outermost electron is much harder to kind of pluck off than it would be for sodium. So in this case, I would say our order here would probably be sodium, and then silicon, and then chlorine. And again, you could back this up with calculating Zeph if you'd like to. Let's just write that up here, just to have it here as our nice answer. All right. The second one says, explain why the lattice energy of magnesium sulfide is approximately 4 times as large as that of NaCl. So if we think about our, let's go ahead and define lattice energy again. So remember that the lattice energy is a measure of the amount of energy that is released when a crystalline lattice is formed. We said that crystalline lattices were very stable because they have that really nice alternating positive, negative structure, where that electrostatic attraction, right, between the pluses and minuses, those different charge, was really strong. And so you would have to add some energy in to break it apart. So for something to have a high magnitude of lattice energy, and we're usually, when we say 4 times as large, we mean in magnitude. So let's just make a note, because we say that a lot as chemists. We'll just say 4 times as large, kind of assuming that we know, we're talking about magnitude, not necessarily the number, because these are usually negative numbers for lattice energy, because it's an exothermic process. Okay, so let's kind of look here. So remember that a high lattice energy is going to mean that lots of energy is released when a crystalline lattice is formed. So, or you could kind of think of it as if there is more energy released when we form that lattice, then there must be a really strong electrostatic attraction between the different ions. So in this case, we have magnesium and sulfur, and then we have sodium and chlorine. We said that there were a couple different things that sort of affect the lattice energy. We said it could be the size of the ions, and it could be the charge on the ions. So in this case, what we probably want to do is take a look at their charge specifically, because that's going to be the real big one here. So for magnesium, we have a 2+ charge and a 2- charge, and for sodium, we have a 1+ charge, and chlorine, we have a oops, what am I doing? We have a negative charge, -1. So in terms of magnitude, MgS is going to be a much stronger electrostatic attraction because they've got that higher magnitude of charge. If you remember back to chapter 8, we looked at Coulomb's law, and it looked something like this. Right? So this is actually why size and charge are, the most important kind of factors here. Size being the distance between the nuclei of the different atoms, so that's given by R, and then types of charge given by these Q values. So if you think about it, if you increase the magnitude of the charges, then that's going to result in a much higher number on the top than if they were a lower magnitude of charge. So because our sizes here are relatively, similar, we can't really compare size-wise, but we can compare with charge. Specifically, we actually have like quantify, like we can actually quantify how much larger. And we can say, oh, that's because we have a higher magnitude of charge. How much higher? Well, 2 times as high, right? Because we're going to take, actually there should be some things here, absolute value signs. So we're going to take those 2's and multiply them together. That gives us a 4 times bigger lattice energy. All right. And of course you would, if you were asked to explain that, you'd probably want to put it into, a succinct sentence. So we could say something like, let me think. The charges of the ions are larger for magnesium and sulfur, so we would have a larger lattice energy. All right, and then this last one says, which of the following ionic compounds would likely have a higher melting point? It says, circle your answer choice and then explain your reasoning in 1 to 2 full sentences and or a picture. So for this, magnesium sulfide, again, I'm not very creative. So looking at magnesium sulfide and barium sulfide. So in this case, let's kind of go back down to our chart here. So we've got magnesium, let me go ahead, magnesium sulfide, and we've got barium sulfide. So really our sulfur is staying constant, right? But the size of magnesium and barium is going to be much different. Which one is going to be larger? Yeah, barium is going to be much larger. So barium kind of looks like this, and magnesium is going to be a little bit smaller. Sorry, these are kind of terrible drawings, but you get the idea. So our size is going to increase as we go down a column, and so if barium is larger than sulfur, we're going to have a little bit of a harder time packing barium as close as it would like to be to sulfur. So that's going to be a little less of a favorable interaction. this means that magnesium sulfide would have the higher melting point because it has stronger ionic bonding than something like barium sulfide, due to that radius. So I would say Mg2 plus is smaller than barium 2 plus. Oh, and here we didn't use charge to reason this out because the magnitude of the charge for these is the same. So really what's changing is this R value here, the distance between the nuclei. So it can, let's say, pack in closer to sulfur, and that results in a stronger, let's be super fancy and say electrostatic attraction. Making it more stable. This requires, wow, I'm wordy right now. This requires more heat energy or thermal energy to melt the substance. That would be probably a pretty good reasoning, and then you could even like leave this picture there just to show your work a little bit. All right, well, I hope that helps kind of review for the exam tomorrow. If you have any questions, just shoot me an email and I'll try to get back to you as soon as possible. Okay.